Well, in this little recording, I'm going to, like it says in front of you there, finish section 10 and start section 11. And by the way, I'm probably going to get a phone call in about half an hour, so you might hear a phone ring and then all of a sudden things will jerk around like I paused it and then restarted it after I finished the phone call. But anyhow, the thing in section 10 that I hadn't finished yet was this stuff about magnetic fields in matter. The last thing I had gotten to was electric fields in matter, how that all the atoms become polarized and kind of line themselves up with the electric field, creating a field of their own in the other direction, so that the net result is to change the effective strength of the electric interaction by a factor that we call the dielectric constant. I forgot what I was going to say. Anyhow, oh yeah, just you get a weaker field out of the same amount of charge is what I was trying to say with all of that, because the field from the matter kind of cancels part of it out. So you get sort of a similar thing going on with magnetic fields in matter. There again, the surrounding material can, in this case, it can work either way. The surrounding material can subtract from or add to the field that the material's been placed in. We'll call the background field B0. Okay, so maybe this piece of material here has been placed inside of a solenoid, or it's been placed near a large permanent magnet or something. Wherever it comes from, you've got this field here that originates somewhere beyond the edges of the picture, and that's where it goes to also. So there are different types of magnetic behavior, and which you get depends on the material. Those three possibilities are called diamagnetism, paramagnetism, and ferromagnetism. And the one I kind of started talking about in the beginning as an example here would be kind of like paramagnetism. But anyhow, magnetic fields come from and are felt by electric currents. Said that before. In a permanent magnet, the currents are within its atoms. The electrons orbiting around the nucleus, also the spin of the particles, all these things produce magnetic fields. Now, in some atoms, it's a nice symmetrical example. I've got some examples written over here. Lead, copper, neon, many molecules, carbon dioxide, are diamagnetic. And in these cases, there is no net magnetic field for the atom as a whole. A copper atom is nice and symmetrical. For every electron that's spin up, there's another electron that's spin down. For every electron going around the nucleus in one direction, there's an electron going around the nucleus in the other direction on an otherwise identical orbit, and everything cancels out. Other materials are not quite so symmetrical. Aluminum, sodium, platinum, there's an expensive one, oxygen. These are examples of paramagnetic materials. Here, the atoms are little tiny magnets. All the internally generated magnetic fields do not balance each other out, but a piece of aluminum or platinum makes a really lousy magnet, because even though the individual atoms are magnets, Well, one creates a field that points that way, and another one creates a field that points that way, and this atom's field points that way, and this atom's field points that way, and this one's that way, and that one's that way, and just a whole bunch of just drawing random errors or arrows in whatever direction comes to mind. And so you have, 10 to the 23rd or 10 to the 24th randomly pointed little arrows, and they're going to pretty much add up to nothing, because for every atom that's creating a field in a certain direction, not too far away is another atom that's more or less in the opposite direction, and they all just add up to nothing. Thermal agitation keeps them all mixed up too. Then there are a few special materials where they can get lined up with each other, but I'm getting ahead of my story. So in a non-magnetized substance, like if you're holding a chunk of aluminum in your hand, you're not going to pick up all the paper clips in a box of paper clips with that. In a non-magnetized substance, these subatomic magnets have random directions, exhibit A, and so when you add them up over the whole object, their total is 0. But what if you place that piece of aluminum in an external magnetic field? So if this external field points in that direction, well, what would happen if you had a whole bunch of compass needles, magnetic compasses sitting on a tabletop? They're all going to try and point in the same direction because of the Earth's magnetic field. Magnets like to align themselves. There's a torque on any magnet placed in a magnetic field. Talked about that a couple of weeks ago. Torque equals mu cross B. Sound familiar? So just like compasses in the Earth's magnetic field, these little guys want to line up with the external field they've been placed in. So like, I don't know, this one right here is going to want to kind of do something like that. And all its friends have similar urges. But I mumbled something a minute or two ago about thermal agitation. At room temperature, anyhow, if you get a magnetic field that's maybe, I don't know, 50 milliteslas, which is a fairly respectable field, you're not going to make these all line up just parallel to each other, nice and neat and organized, because of thermal agitation. The better analogy, instead of a bunch of compasses on a tabletop, is a bunch of compasses in a cement mixer, okay? If they're getting thrown around and bumped into each other and, just constantly agitated, that's going to make the alignment with this external field very poor. As soon as they start to swing around and line up, something knocks into them and throws them off. And so paramagnetism is a fairly weak effect, but it will add a little bit to the total magnetic field. So the total magnetic field inside that piece of material there will be, as usual, this is a little out of focus, but I think you can just barely read it. But that says B0. That's this external field here. Plus B mag, that's the magnetic field generated by the atoms of this material. Okay, to the extent it gets magnetized, that creates a contribution to the magnetic field that gets added on to the external field to give you a total that's a little different, or sometimes a lot different. So B mag is the field due to the object's magnetization. How magnetized the object becomes depends on how strong the background field is. Probably not too surprising. If you place this in a strong field, it becomes more strongly magnetized than if you place it in a weak field. So it depends on the background field and a property of the material called its permeability. So this is just like when I was talking about electric fields. I said how that epsilon replaces epsilon naught anytime the field exists in a material substance. Well, it's the same with the magnetic permeability. Mu naught is the permeability of empty space. Okay, so that's what you stick in the equations if you're talking about empty space, which is what we had been doing up until pretty much right now. It was always magnetic fields in a vacuum. If the magnetic field exists in a piece of lead or a piece of aluminum or a piece of iron, then some other value for the permeability goes into all those equations rather than the permeability of a vacuum. Whatever medium the field is in, that's the permeability of that medium belongs in Ampere's law and everything else, Maxwell's equations. If it's a vacuum, use the permeability of a vacuum. If it's aluminum, use the permeability of aluminum, and so on. So I said all that. Different materials react to being in the field in different ways. Diamagnetism. Well, all materials have some diamagnetic behavior. Whether it's lead or whether it's iron or whether it's aluminum, you get diamagnetism in everything. It's just if one of these other effects is also present, it's stronger. And so the diamagnetism gets kind of pushed aside and overwhelmed. But if you had an atom with no magnetic moment, it will develop one anti-parallel to that background field. Okay, what happens, if you've got like a copper atom, for example, as the electrons move around within the atom, they feel that QV cross B force. Well, if you've got one electron that's going around in one direction, maybe that force is toward the center of its orbit, toward the nucleus. You have another electron which is going around the same sort of orbit but in the other direction. Well, if you reverse the direction of motion, you reverse the direction of the force. Magnetic force would point outward rather than inward. So for one of the electrons, the magnetic force tends to speed it up because you've increased the centripetal force on it. And for the one going in the other direction, you've decreased the centripetal force. So that one gets slowed down. And there goes your symmetry, okay? So the atom develops a magnetic field, even though it would not have had one if there was no background field, if it hadn't been stuck inside of a solenoid or something like that. And if you work through the details of it, if this is the direction of the field here, pointing toward the right, the magnetic fields that the atoms develop point the other way. So with opposite directions here, the total is going to be less than the background field, but not by much. We're talking about a parts per million kind of thing here. Like I said, it varies between different materials, but something down in that range. So B total is slightly weaker than you would have had if you weren't inside this material. If that wasn't there, and if you were just out in empty space, that's what B0 is, B naught. So the total field is slightly weaker than that. So Diamagnetism is a repulsive effect. You think of magnets as attracting things. Well, that's how ferromagnetism works, and that's the familiar example. You get a bar magnet, you stick it in a box full of paper clips, pull it out, and there's paper clips stuck all over it. But diamagnetism is repulsive. You can actually see that if maybe you remember doing the gravitation constant lab last fall. If I get out, if anybody's really like absolutely dying to see this, I can get out one of my Cavendish balances. Actually, I have to get out the old one. The newer ones are made out of something else, but the one that I've had for years, the little lead balls in there are made of lead. And of course, it's suspended from that ridiculously sensitive balance. And you hold a bar magnet to that, and you can see it starting to rotate right away from that magnet, getting pushed away from it. Maybe for a more dramatic example, go to YouTube. This is actually like one of my favorite videos in the whole world because it's such a nice illustration of one of my favorite quotes in the whole world. Maybe you've heard me before quote Arthur C. Clarke and say, "A sufficiently advanced technology is indistinguishable from magic." Among the things that are diamagnetic are water molecules. And water is the main ingredient in lots of things, including small frogs. So I guess they must have just been fooling around with the magnet on their lunch hour or something. I don't know. But somebody a number of years ago made a video. It's a short video. It's only like 8 or 10 seconds long. Just go into YouTube and just put in the search box levitating frog or something like that. And what you'll see is you're looking down into, I'm pretty sure it's a superconducting magnet. Somebody's got a big solenoid made out of superconducting wire, because that's what gives you a really strong magnetic field. And there's this frog just floating in the magnetic field, kind of flopping around and like, hey, what's happening to me, you know? And I'm sorry, levitating a frog is something straight out of Harry Potter. So sufficiently advanced technology is indistinguishable from magic. Yes, magic is real. It's just all the people who go around muttering incantations and waving wands and things don't understand how it works. How does magic really work? Start by learning calculus, and then you take a physics course. And then someday, if you work really hard, you too can levitate frogs. I think they did a strawberry too. I'm not sure about that. But get off my soapbox here and get back to the notes. Paramagnetism. So these are materials where the atoms do have a net magnetic moment. And this, I was telling this story, 5-10 minutes ago. You place them in the background field. They try to rotate like compass needles and align themselves with it. But thermal agitation prevents good alignment. So actually, paramagnetism is not an awful lot stronger than diamagnetism. But in this case, it's, the magnetization is parallel to B naught instead of being anti-parallel. So you add rather than subtract off. And finally, there's ferromagnetism, which is actually kind of a long story that I'm going to try to summarize here. But if you've got a nail, okay, and you were to kind of magnify it enough that you could look at the individual iron atoms in it, you'd find that the iron atoms are all lined up with each other, nice and neat and pretty, kind of like that, in small microscopic regions called domains, okay? The quantum mechanical effect, I think the name is exchange coupling, if I remember right. I'd have to look that up before I swore to it. But a quantum mechanical effect overcomes thermal agitation, and makes all the atoms line up in these little regions called domains. But the reason the nail is not a magnet is because the domains have different random directions, and there's a lot of domains in the nail. And so in the end, it's kind of like the paramagnetic material, where they don't, they cancel each other out because of the random directions. But if you place it in an external field, so I mean, the simple elementary school way to make an electromagnet is you get a big nail, probably a railroad spike would be better than a little nail like you'd use in carpentry, but you get some sort of a big chunk of steel or iron, and you get some insulated wire and you wrap it around there a lot of times, and then you hook it up to a battery like you might use for a camping lantern or something like that. And then when it's hooked up to the battery, it'll pick up some paper clips, and when you disconnect it from the battery, it drops the paper clips. So what happens is when you send current through that coil that's around the spike, that external magnetic field makes, first of all, it makes the atoms within the domains try to align with that field. So you've got the compass needle thing going on again. If the field points to the right, these guys here will start trying to do that. In addition, some of the atoms, as I understand it anyhow, some of the atoms that are along the domain boundaries will switch over to more favorably oriented domains. Like these guys here are already pretty well aligned if there's a magnetic field pointing to the right. So this atom that's right on the edge says, if I join up with these guys, I can kind of relax. I won't have this torque twisting on me all the time. And so anyhow, in a magnetic field, you get alignment. And this time, it's some pretty serious alignment, okay? Unlike a paramagnetic material, where it makes just a small difference. You get the right alloy, and the total field can be as much as 1,000 times the external field that the piece of iron, well, there's about half a dozen different materials that are ferromagnetic. The two that you hear about the most are iron and nickel. Any of you who know trivia about coins might be aware that Canadian money, unlike American money, is magnetic, okay? If you've got a Canadian nickel and an American nickel sitting next to each other on a table, and you come along with a good strong magnet, the Canadian nickel or dime or quarter will hop off the table to the magnet, and the American one's just going to lay there and go, no, I don't feel like it. Because American coins are actually mostly copper, okay? But as for the Canadian coins, well, it depends on how old it is. If you go back like about 30 years, Canada was producing a lot of nickel. They were one of the world's major nickel producers, and their nickels and dimes and things had a very high nickel content, and enough to make them magnetic, where they would jump off a table if you had a strong magnet there. And then, yeah, they kind of started to not have as much nickel as before. The price of nickel went up, so they switched over and started putting steel in there instead, and I think they just coated over with something else. And that was sometime in the 1990s, I think. And so the newer ones leap off the table because they're made primarily out of steel, which is actually slightly more ferromagnetic than nickel is. Cobalt is ferromagnetic, and 3 other elements that I can't remember because nobody's ever heard of them anyhow. They're those weird ones that people don't talk about. But whether or not, you see, if you make an electromagnet out of a railroad spike, when you turn the current off, so the external field goes away, then thermal agitation knocks them back to where they were before. They very quickly re-randomize, and the domains start having random directions like in this picture here again. Or maybe they don't. Depends on the alloy, okay? which means like if you're talking about iron. Well, what have you mixed in with the iron? You know, it's kind of like making spaghetti sauce. This person likes a little more garlic. This person puts in a lot of oregano, you know. And if you're making metal, you know, you've got this melted iron in front of you. Well, we'll put in a little cobalt and we'll put in some nickel and you know, maybe a little chromium and stir it up and see how it smells. And I'll put in a little more chromium. And so that's what I mean by the alloy is, you know, there's all different alloys of steel and other materials. So depending on the alloy, when you turn the external field off, the domains may relax back to being randomized again, or they may get stuck once you've lined them up, okay? The effect is called hysteresis, which is, I mean, as far as the roots of the word, it's related to the word history. It means the state of the material is determined by what happened to it in the past. A material that has a lot of hysteresis is good for making permanent magnets. It's good for making magnetic information storage, like audio tape, videotape, magnetic discs that you would use with computers. For any of those types of applications, you want a lot of hysteresis, because once you expose it to a magnetic field, you want it to stay magnetized. You know, in the case of like a videotape, you want it to stay magnetized for decades. You don't want the recording to kind of dissolve. On the other hand, for the iron that you put, for example, in a transformer core, hysteresis is very, very bad. You want an alloy with as little hysteresis as possible, because as those, you know, you've got an alternating magnetic field, typically 60 cycles per second, shaking these domains back and forth. And as things, you know, the keep churning around in there, it generates heat, which takes energy away from what's going to make it to the secondary coil. It makes the transformer inefficient if the core has hysteresis. So that's a quick tour of magnetism in matter, a subject that might be an entire chapter in a more complete course, but, well, you know, that's what upper division courses are for. Section 11 starts out with LR circuits. So LR as in an inductor and a resistor. And it's a DC circuit. We're going to power it with a battery. And I've got this two-way switch here, double pole switch. Let's say that the switch starts out at position A, and it's been there for quite a while. There's a current flowing around. Then at t equals 0, all of a sudden you throw the switch from A to B. Okay, we're going to assume that the switch makes contact at B at exactly the same instant that it loses contact with A, which would be a tricky thing to do with a mechanical switch, but is extremely doable with some electronic type of switch, you know, a transistor or something like that. So basically, when I throw the switch, it takes away the battery. There's still a complete circuit for current to flow around, but there's no longer a battery supplying energy to replace what's being lost to heat as the current flows through the resistor. So obviously you take away the battery and the current stops flowing, but it doesn't stop instantaneously. There really isn't anything that happens truly instantaneously. There's a transient period. Whoop, there's my phone call. Where's the pause? Okay, well, now it's 15 minutes later for me than it was for you a couple of seconds ago. Let's see if I can remember where I left off with this. So you throw the switch, it removes the battery, and the current starts to taper off, but it doesn't go away immediately because there's a lot of energy stored in the magnetic field of this coil. And that energy gets used to maintain the current for a while, okay? You could think of it in terms of Lenz's law, that once the current starts to drop off, the self-induced voltage here, remember, self-induced voltages don't like any kind of change. Whatever's changing, they're against it. So if the current's on the way down, the coil is going to induce a voltage in a way that keeps pushing it through. And so that self-induced voltage maintains the current. When we get further down the page, we'll see that if the current's building up, the self-induced voltage holds it down. But if it's on the way down, the self-induced voltage holds it up, because the strength of the magnetic field is proportional to the current. If the current's getting weaker, the magnetic field's getting weaker, and the energy that was in that field has to go somewhere, so it goes back into the circuit and gets used pushing the current around. If the magnetic field is increasing because the current is increasing, there's energy getting added to it, and that has to come from the current that's flowing through there. So in that case, it draws energy out of the current, and that means the voltage would be the other way around. So anyhow, I'm supposed to show you why this equation here is true, and just give me a second here. Okay. So without the battery, section 11, without the battery, what you've got is just a coil and a resistor. And I'm going to use a lowercase I for the current this time. It's flowing around like that. Inductance L, resistance R. The loop rule. Says that if I add up the voltages around this loop, the total has to be 0. Okay, the voltage across the inductor is minus L times di dt, and this is just like, you know, as far as the plus and minus signs go. Yeah, I still got it here. Here's the page I wrote the other day when I was doing this problem back in section 3. Minus here, minus there. Same thing that I'm doing now. So minus IR, Ohm's law, equals 0. Voltage across the inductor, voltage across the resistor. Of course, di dt would be negative if the current was decreasing, which is the case we're talking about here, and that's how it adds up to 0. Anyhow, a couple lines of, we got minus L di dt equals IR, and then it's kind of good to collect all the constants together in one place and all the i's together in one place, and di over I is equal to minus R over L dt. So multiply both sides by dt, divide both sides by I, divide both sides by negative L, and the end result of all of that is what I've written here. So this is the differential equation that governs this circuit. Okay, it's about the simplest differential equation there is. It's a first order ordinary differential equation that you can just solve by separating the variables, which is what I just did. I've got all the i's on one side and all the t's, well, there's only one t anyhow, on the other side. And once you've separated the variables, you can integrate both sides of the equation, which I think I'll do over here because I've got space on the page over here. So integral of di over I equals, now the resistance and the inductance, they're just numbers, you know, like if that's a 400 ohm resistor, 400 is just a constant. And I kind of tweaked the camera there. So minus R over L integral of dt. Limits of integration. What's on the bottom on one side has to correspond to what's on the bottom on the other side. What's on the top over here has to correspond to what's on the top over here. So at t equals 0, that's when the switch got thrown. At t equals 0, we'll call the current at that moment, the original current, we'll call it I0, as in the current at t equals 0. At some later time t, we'll call the current then I without a subscript. And what I sort of had in mind for the notation here is, you see the capital I is one of the limits of integration, whereas the lowercase I is the variable that's, you know, the current is changing moment by moment. And I suppose really, now that I think about it, I should have done the same thing over here too and had like a big T and a little t, because this is a constant and this is a variable, but I wasn't that careful. Anyhow, as I imagine you know by now, the integral of di over I is the log of I, natural log to be precise. You get into some more advanced courses, and I mean, I've got textbooks in my office where they just use log for the natural log. So if you know, if you're in some other course someday, don't get thrown by that. There are some authors who just assume, you know, well, if you're talking about a logarithm, of course you're talking about a natural log. What other kind of log would you be talking about? But anyhow, R over L, and the integral of dt, of course, is t. So you have to evaluate at the upper and lower limits of integration. And, you know, lower limit, this is just equal to 0. I won't bother writing that down. We have this. A few more lines of manipulations. To make this a little tidier, this is using a well-known property of logarithms, which if it's not quite so well known that you know it, you can find it on one of the back pages of your reference handout. But hopefully from some intermediate algebra class or someplace like that, it looks kind of familiar to you that the log of A minus the log of B is the log of A over B. Well, my objective here is I'm trying to get the current as a function of time. Okay, as I've probably mentioned before, an algebraic equation is one that you solve for a number. A differential equation is one that you solve for a function. And the question I'm trying to answer here is, what does the current do as time passes? And, you know, the answer to a question like that is a function. So I'm trying to solve it for I as a function of t. I got I got to dig the I out of there. The way to get a function off of something is to hit it with its inverse function. So, exponential function of both sides. Another thing where you see some variation in the notation, in some textbooks, instead of e to the x, they'll write it exp for the exponential function. Means the same thing. Well, a function and its inverse function cancel each other out. That's like when you square a square root or something like that. So this over here is just I over I naught. And finally, just multiply both sides by the original current. And that demonstrates that what the current is going to do is an exponential decay, an e to the minus x kind of thing, as written in smaller but better writing here. Now, here's a graph of it. You should be familiar with the exponential function from some math class. It's got an asymptote. This is e to the minus x. Okay, if you had e to the x, the asymptote would be over here on the left, and on the right, the thing would be heading for the sky. But e to the minus x, it kind of flips it over. You know, right becomes left, and so on. So the exponential function would be real big. E to the minus x would be real big over here to the left, but that is irrelevant because it doesn't start obeying this function until t equals 0 anyhow. That's when the switch got thrown. And as time passes, the current gets smaller and smaller and approaches 0 asymptotically. So if you ask a question like, how much time does it take for the current to stop? Well, technically, the answer is never. I mean, eventually the current's going to get so small that you won't be able to measure it anymore. It's gone for all practical purposes. But there isn't a well-defined moment when it's gone. It just sort of fades out. And when you don't notice it anymore, depends on how sensitive your meter is, I guess. So if you want to have some way of comparing, you know, it's like this circuit turns off really quick. This one lingers for a while. If you want to have some way of making those kinds of comparisons, you can't just talk about how long does it take the current to stop. What is a sharply defined amount of time is how much time does it take to get down to 37% of what you started with. Why 37%? Well, it's actually not exactly 37%. That's been rounded off to the nearest percent. It's actually 1 over e, where e, of course, is the base of a natural logarithm. Every once in a while, I get somebody who wants to stick 1.6 times 10 to the negative 19th in there. We are using the letter e for entirely too many things, I suppose. But why that particular amount? You know, why not 21% or something like that? Well, I'll show you in this little corner that's left over here. So time to reach I equals I naught over E, which is, when you round off a little bit anyhow, approximately 37%. Well, let's take this function that I just derived. And for once, I did do a proper derivation rather than just kind of demonstrating something for a simple special case or something. So fill in for I the thing that I is equal to. I0 times e to the, e to the negative 1 power is the same thing as 1 over e. So this is just another way of writing that. So I0 times e to that power equals I0 times e to that power. Well, hopefully it's fairly obvious that the powers are equal. Minus signs cancel. Multiply both sides by L, divide both sides by R, and L over R is the thing that I wrote up there. L over R is the time to reach 37% of the original current. So the reason we use 37% and not 21% or 17% or some other number is that it's really easy to calculate. You just divide the inductance by the resistance. If you wanted to calculate the amount of time it took to get to 21% of the original current, you'd have 0.21 equals e to the minus r over lt, and you'd have to solve that for t, and it would be much messier. Just r over l, and so that's why they do it that way. So it shows up on the graph here. You start out at t equals 0 with some original current I naught. When the time equals L over R, you're at 37% of that. And at two time constants, 2 times L over R would be about there, and you would be 37% of 37%. It'd be I naught over E squared, and so on. That's the way exponential decay works. This amount of time is called the circuit's time constant, and we're going to represent it by the Greek letter tau. So e to the minus r over lt, if you're going to represent the time constant with a tau, r over l times t, that's e to the negative t divided by tau power, which is small enough you probably can't read it on the screen there, but well, anyhow, that's what it says. If you can't see it, write it down somewhere. E to the minus t divided by tau. Well, you've got your formula sheet. You ought to be able to read it on there, even though you never got this note packet. I'm going to have a big pile of these until next year, I guess. What if the current is building up rather than being turned off? Well, it's the same story pretty much in reverse. I could write another differential equation. It would just be slightly bigger than this one because you'd have to have a term for the battery as well as these two things. I could go through a similar type process. By the way, some devious professor gave you a problem similar to this in the homework with the idea in mind that the idea of a physics course is that you should actually understand the physics as opposed to just throwing numbers at formulas all the time. So what I did is I made up a problem. Yeah, I have to admit, I didn't even steal this one out of a textbook. I just made it up myself and stuck it in the homework, where we have some sort of non-ohmic material here that doesn't obey Ohm's law. I forget exactly what I did to it. I made it like I squared times R or the square root of I times R. I messed with it a little bit. And I said, what's the current as a function of time then? And what I want you to do for that homework problem is pretty much what I just did here, except you won't have the same function because it's not I to the first power. It won't come out a natural log anymore. It'll be something else that isn't any harder to calculate than this. It'll just be different. So I took this and gave it a little tweak and made it into a homework problem, and you should be expecting that when you get into assignment 11. But anyhow, if you're turning the circuit on rather than turning it off, well, it's just a minor variation on the same story. Instead of saying, well, the current doesn't go away instantaneously, it's that the current doesn't reach its final value instantaneously. Once again, it builds up to an asymptote, just this time it builds up to it from underneath instead of coming down on the asymptote from above. This is the exact same shape as that, except it's been flipped upside down. If I had one of my transparencies like I use on the overhead projector, I could just flip it over. You could see through it from the back, and this graph turns into that graph when you do that. So same time constant, L over R, and it means the same thing, which is how much time to get 63% of the way from where you started to where you're ending up. Okay, here it's 63% of the way down, which is to say 37% of the way still to go. Over here, it's 63% of the way up. The final current, if you leave the switch at A for a long time, like, go have dinner and then come back and see how it's doing, the current's going to be given by Ohm's law, because while you're eating dinner, this thing probably went through something like, a million time constants. And it has long since reached a perfectly steady current. Well, a perfectly steady current induces nothing. The IDT term is gone, okay, because the IDT is 0. So at that point, all you have is a battery and a resistor, and it's just I equals E over R. To steady DC, a coil is just another piece of wire. It's only when the current is changing that you get a voltage induced here. So this final steady state current that it builds up to, or for that matter, the initial current when you first threw the switch on this, would be the same thing. It's Ohm's law. Amps equals volts divided by ohms. E over R. EMF divided by the resistance is what it builds up to. And instead of it being an e to the minus t over tau, it's 1 minus e to the negative t over tau. The 1 minus is what flips the picture upside down. So I'm going to do a sample problem, and then I think I'll say I've gotten far enough for today. And the next time we have one of these one-sided conversations, we'll talk about RC circuits on the next page, which actually do just about exactly the same thing as what I've just been talking about. But, well, I guess I was going to save that. So, fresh sheet of paper, 11:1. So the switch is left today. It's the same picture as at the top of the page. I've just filled in some specific numbers. It's left at A for a long time, which means the current reached the value given by Ohm's law. Then it's suddenly thrown to B. How long after you throw the switch until the currents drop down to 50 milliamps? So I equals I naught e to the minus t over tau. And the question is to solve for t. How much time until the current is 50 milliamps? Now, maybe one heads up I should give you is that a mistake I've seen quite a few times, actually, more often than you might think, is you've got these two equations. One is for when the current's being turned off, the other is for when the current's being turned on. And they're labeled that way on the formula sheet. It says current decay, and that's written there. Current building up, and that's written there. And people grab the wrong equation. When it's doing that, they use this. When it's doing that, they do that. So think carefully. If it's been left at A for a long time, you have an existing current, okay? Because when the switch is touching point A, the battery is part of the circuit, and that's going to make the current go around. And I guess I should have this up here where it shows on the camera. So batteries in the circuit, current's going around. And so you've got an existing current. And then when you take the battery away, that current is going to decay. It's going to decrease towards zero. So you want to be grabbing that equation. And then we got to fill a bunch of stuff into it. So the steady state current that existed before the switch was thrown. Ohm's law. The EMF divided by, it's not a very good E, is it? But, well, if I tell you it's E, you can cope, I guess. If this was the Middle Ages, I probably wouldn't have made a very good monk sitting there copying the Bible all day long. You know, it's like, is that a B or a 6? Two amps. That's what was going around there at the instant that you threw the switch. So that's what's going to go in. You can think of it as O for original if you'd like to. That'd be one way to do it. And the reason, once again, is maybe I'll draw a little picture. What you have once you've reached a steady state, that's a little better. You've got the battery, and you've got the resistor, and you've got this current I naught going through the wires. And again, a coil is just another piece of wire if the current is steady. No induced current no induced voltage if the current is steady. So this comes from that. As for the time constant, convert millihenries to henries. Five ohms is my resistor. And so 0.00400, I suppose, of a second. So filling stuff in now. How much time until the current reaches 0.050 of an amp? That's how much current is flowing at the time t that I want to calculate. So that goes in for I. And I've got 2 amps, e to the negative. Well, I can leave this in seconds, or I can convert to milliseconds. Whatever unit I put in for the time constant, that's the unit I'll get out on the time. Maybe I should leave it in seconds and not confuse matters any more than I have to. So that goes in there, and the 2 amps goes in. Anyhow, we got to solve that for t. Well, solving any equation, really, is a matter of peeling away the layers around your variable. As somebody probably said to you in elementary algebra, you have to isolate the variable. We have to manipulate the equation around until it says t equals something. And the outermost layer that we have to peel away from that T is this 2 amps. So divide both sides by 2, and I've got 0.025 equals e to the negative t over the time constant. Next thing that we have to peel off, what's the outermost layer now is this exponential function. And as I already said when I was doing something a little while ago, the way you get rid of a function is to hit it with its inverse function. So the inverse function of an exponential is a logarithm. Take the log of both sides. And maybe I won't bother writing that out, but the log and the exponential cancel each other out. Function and an inverse function kill each other off. So you've got t over 0.004. And then finally, I need to multiply both sides by negative 0.004. And then it's calculator time. I don't know as you necessarily need to write this down, but just in case anybody needs to compare. The natural log of 0.025, you should, if you're pushing the right button, you should get that. Minus cancels minus, which is good because the time should come out positive. A negative time would mean before you threw the switch, which is not really, that doesn't make a lot of sense. And so you multiply, and it's 0.0148 of a second. And that's all from Physics Land for today. Pretty soon I'll make another one of these. We can do some more. Always a good time.